I have to thank the organizer to give us this fantastic opportunity to speak here. I have a very hard task this morning because I'm the last speaker before lunch, so I have to be entertaining and at the same time very brief and fast. I will do my best to get into business so quickly. So we are working on automotive projects and as well on climate science projects. Here I will relate to automotive science. And this is a Nature paper that came out 2 weeks basically ago, where the people said, okay, they compared data for autonomous driving. So they want to have an AI that drives autonomously. And to make it short, the story was, we don't have enough accidents. We don't have enough data on accidents. And we should think this is a good thing. But indeed, how can you train an AI to avoid accidents if you never have accidents? So that is, of course, something where we heavily want to understand how our neural networks in that case work. But it's general things I think we can discuss, but I will focus on neural networks. So these are basically the main things I want to go through. What is machine learning in the presence of imperfect data, distortions. Then I come to phase transitions, and this relates a lot to what we had before in the 2 talks before, only that we don't generate, we only take the diffusive part. Yeah? And we figured out that it's important to have a tool set where we can reproduce our machine learning, and then I will come to the example at last. We had this figure already this morning, so that is the way for generative AI. So if we generate data, we understood everything now by having listened to the previous talks. That was very good, very instructive. But we as well want to understand what happens if we learn, if we have learned something, and then what happens if we apply an already trained network on noisy data. So the data we have for inference when we really apply the models might be of less quality than the data we have trained our network with. And on the other hand, can we train a network with not so perfect data? And what happens if we apply then the data to perfect data? Of course, in the context of autonomous drive, it's clear you have sensors. The sensors don't work. I mean, it's like our eyes getting worse. If we drive with 18, it's good. If we drive with 60 or 80, sometimes the sensorics doesn't work again as before, and the people start driving with 30 kilometers per hour, or I don't know what this is in miles. Yeah. So we made this experiment. I will come to the details later. So what we observe when we increase here the noise on the data. So we did what we heard before. We just applied Ornstein-Uhlenbeck process to the data, made them noisier, and then I will show examples later again and again. So here we just make the data more fuzzy and more fuzzy. What happens is we observe a transition from more or less acceptable recognition to basically 0. We took a known system for that, where we knew that we have enough data and we have large enough networks, and we can maybe as well scale the networks. So this reminds on phase transitions. A phase transition is known in physics. I will come to it in a second. What we took as a network, we took the efficient net. It's a CNN that basically scales with the task in width and depth. So from theoretical arguments as well, considering the normalization group and phase transitions, one actually can think that this is a good strategy, because if the ratio between width and depth stays more or less constant, then you can scale up your system and it will contain and conserve several properties which are important. So I will make a quick rush with you through physics. Apologies for that, but I think it's good to draw these analogies. Everybody or many people might have already seen that. So we have a Hamiltonian here, which describes the interaction between spins, which can be 1 + 1 or -1 or +1/2 and -1/2, depending on the setting. And here we have an external force. And when we crank up temperature, noise makes our spins flip up and down. Then we observe that magnetization of a material, which in theory is infinitely big and infinitely long, so volume is infinite. We have infinitely many spins here, and the driving is as well, the external forcing is as well acting on the whole domain. So we can have a transition from this is a very organized state to a very disorganized state. And in the middle, right here, we have so-called domains which form where the material is, so the energy we put in by temperature is not enough to destroy the order. So we have some domains which are ordered, others which are unordered. That is basically what happens. And how does it relate now to our phase transitions in neural networks? I want to dwell a little bit on the driving force. So this is when I have magnetization and I change my driving. You might have already guessed, driving is data which I apply to the network. So I drive a network, I force it. It's similar to what we had this morning. So x0 in the Chris terminology would be the data which we drive the network with. So what happens if we change the network, the driving, and this is the whole thing. If we make our data noisier and noisier, then we can get the transition here from learning to not learning, from cognition to no cognition. So the data might be deciding if we have a good recognition on our network or not. For the interesting, so these things we discuss are called continuous transitions, and they have criticality and universality involved. Universality means that by studying very simple systems, we can draw some quantitative results for very complex systems. So that is in the terms of magnets. If we have these spins, that's of course a very simple idea, but we know from reality that our building blocks, these are molecules which are very complex, and we have very, very complicated things involved with building the molecules. We heard that in the previous talk. When we have proteins folding, of course, we make an idealized model. So these are all the things that we can consider here. What do I have to? I don't even see it here. It's not on my screen. Ah, it's on this screen. It's gone anyway. So it was threatened. Got scared. So here we have a score. We have derivatives of an order parameter. And then the things I focus on in this talk are data and the noise on the data. So this is the external field I force a material with. So I force a network, and I want to see how does the network respond to forcing. And this network is already trained in our setting, so we have a trained network. So we ran through all the training, and now what happens if I feed my trained network with crazy data? You might ask what's temperature, thermal noise. That is, it took me quite a while to figure that out. It is what makes our spins flip, what makes our sets, our weights. It's the stochastic, it's the gradient search. That can be stochastic or not, but this makes our things flip. So we run and run over, and while iteration, we change our weights. So that's basically the equivalent of thermal noise, which doesn't play a role in these considerations now. But the important thing is we have a critical slowing down. So that means as well, if we have bad luck, our data don't fit our model, we take quite some long time, in principle, eternally long, to converge. So if we stop there, it's just a snapshot of having weights which are like this on one side, like that on another side, and in the next step, they might flip all over. that is very important. It's a very interesting observation. And on the other hand, the last thing we want to mention that again, so we have actually always a score which we want to minimize. So this thing should, in principle, go, yeah. So of course, this is a mathematical conference, so I don't contain too much math on these slides, maybe only these few numbers, but it's they built the ingredients. So here we have the so-called free energy. That's the thing we minimize. And here we have the partition sum. This is exactly the normalizer we had in our densities in the previous talks. Rho over Z. This is the same Z. Yeah, it's the partition. We count states in our material. We count our spins, the configuration, and this is called a state. And they can be very, very how is that called and arted? I forgot. You can have one state with many configurations. Yeah. So if, as an example, if you feed in a 0 in a network and want to have out 0, then in between your network might be very large and it can do whatever it wants, as long as the last layer, if you have a fully connected layer on top, if you have weight 0 there, the rest of the weights can do whatever it wants. It can hallucinate as much as it wants. And still the result will be precise, 0, 0, or any constant. So then this will be a very broad distribution. On the other hand, if you have these distributions we saw that should be peaked, then we have here this log Z will be much smaller. So that is essential. And then we have these analogies of the magnetization, which corresponds to our score. Our external fields are the data. It's a D. I didn't figure out a better symbol. We have temperature. I have a double symbol here because it's kind of, I ran out of symbols actually. My fantasy stopped here. Interesting as well is correlation length on the transition. All the weights tend to be correlated. And so, what, apart from these things, I'm on the way to investigate universality. We didn't do it, but that is the main point about all the things. If there is universality in all these coefficients, this is what happens at phase transitions, at these very large systems. If there is universality, we have very strong and general results, and we may obtain them by studying simple systems and then apply them to many classes. Say if we find out that say LSTMs or multi-layer perceptrons just behave the same like a multi-layer perceptron, then we can study that and have asymptotic results on that. And then the details will be worked out on the concrete material like a transformer or autoencoders, which might be very complex. So what happens if we have a finite amount of data? And what happens if we have not an infinite number of neurons in our system? These are very important questions for any application. So we know that we have a scaling of the width of this transition. It will become very broad for very small networks. So if this length L, which is just the total of sum of width and depth, if this size is very small, then this transition width, which we have here, yeah, just to say it again, so we might have different lengths. So this thing will either look like this or like that. This is for small l, this is for big L. So this is important to know for any realistic things. Same for the points of the transition, the time to convergence, important as well for our algorithms, and the correlation length. How does it look like? We made numerical studies. You know that already. We applied the Ornstein-Uhlenbeck noise. So we start from a certain configuration, add Langevin equation. We have a Langevin equation here. So It's not formulated, so this is of course not in a stochastic way. I'm a physicist, so this is the physics way to write it. It's of course stochastic equation. So dx equals minus x plus dw. Yeah? And we have white noise here. So we add that, we do that, and we want to study in particular scaling, finite size effects, and if there's universality. These are the results for many efficient nets. So we took these efficient nets from 20,000 to 400 million nodes in the network. They scale, so there's a, and then the question is, what can I say about this behavior? And what can I say when I go up and crank up the number of nodes in my model? As you as well see here, this is very unsatisfactory. We took the ImageNet 1K data, this is 1,000 classes and approximately 14 million data points. So it's not the full data set, but large enough for us. These, our studies ran on the Jülich supercomputer, so it's a pretty big computer where we had some projects going on. They take quite some time because we run here through many noise steps. So what do we observe? So that looks pretty unspectacular. When I saw it, I was very happy actually. So we have here very little, a very small network, and here we have a very big network. This is all efficient net, as I said, from 20,000 to 400 million nodes. I think it was million. And means 3 decades, more or less. And that is important to see scaling. If you have scaling, I mean, this is a log-log scale. If here on the log-log scale, you often see plots where this goes from 4 to 5. 1 decade doesn't mean scaling. A power law needs more than 1 decade. And that took us long simulation time, actually. So we have here a pretty nice scaling with 1/3, and this is a classical exponent for scaling laws and phase transitions, for finite size scaling, for exactly the width of this transition. So that's what you see here, that gets broader and broader. Of course, this is as well worse. And so it gets better and better if you have more and more nodes, but at a certain point it saturates. So that is this is the first indication of universality and criticality. And what we do now, while I'm talking, Thomas is running the code for visual transformers, doing the same task, fulfilling the same task. We had as well some ResNet 50 runs, which I don't show. They look like these ones. So it doesn't add on information I can show you. It just supports what we already saw. But it's not conclusive because the ResNet 50 was not on the scale we had here. So we decided that we take whatever is recommended. It was a bit harder to scale the systems. What is the practical aspect on it? So we ask, given an objective, the model, and an infrastructure, hardware, we want to have a model that fits on our hardware. This is the applied aspect. So I go to inference, I have to deploy my autonomous driving AI to a car. So the car, of course, is no compute center. So what happens now? So how much data do I need? How much data do I need for training, and what do I need to get a real result which I can apply? So this is, of course, a graphical indication. In reality, we do that by computer. We choose a bound, we say, okay, I want to have 99% of all tests of all data to be recognized nicely. No pedestrians to be driven over. And then I can find a certain noise where my car has to stop. Yeah, so I say, okay, it's sensorics, doesn't work, please stop. That's what we do as well. If it's winter, it snows. Doesn't snow in all parts of the world, but if it snows in winter, or if it's very dry, you might have a sandstorm, whatever. Then you stop after a certain time because you don't see. Your sensorics is limited, and then your natural intelligence, of course, stops to work. says, I can't drive anymore. I expect any artificial intelligence to do the same. So the computations we have to do now are, we compute the partition sum, we compute the free energy, we can compute the mean quantities and their fluctuations. This is what we are currently doing. I can't show you results on that. So when we have done that, we can, of course, then compute the Boltzmann probability and minimize f. And as a result, we should see that we can do these phase transitions as well in a numerical way supporting that. But I guess I have to dig into Lorenz's stuff, what he did, and maybe this is pretty much aligned on what we have to do now. When we developed this whole thing, we said, okay, what is a machine learning system is actually code or model, it's the data, and it's the hardware. And to reproduce a result, I need all three of them. It doesn't help if I have a code which doesn't run on your computer, or if I have data which you can't grab. So in science, it would be very desirable to have a system where I come, like in GitHub, GitLab, I tell you, okay, there is a commit hash, take the hash and run the system as is. Data are loaded, the model is loaded from wherever you have it, and you have to run it on the same hardware. So it doesn't help if we make inference on an embedded chip when it's designed for, say, a laptop or a compute center. This is, so we sat down, this goes back many years, and said, okay, let's version data and hardware and the code and give this a version such that it's easy to collaborate. That's what we did. So it's a kind of ads, but I think it's important to understand, at least we found it very important. We built that tool for HPC pipelines, but of course it works on any cloud and as well on your computer. So it connects to run ML jobs and the results. So then we go and have here code data and our runs on a certain machine. We have our runs, which are called inference here. That's what we do. And we get our runs here either on Colab or on the local infrastructure. And this is exactly what we did here. And at the end, we can collect the results for many models. I don't click through, but we think we have created a nice infrastructure here to handle the machine learning models. So you are invited to come to the platform and try it out. We will be happy to assist. I promised an application, last 2 or 3 minutes. I ran through it. So I said, we need more accidents. So what we did then is in the course of these projects, yeah, that was my student saw it and he said, oh, that's the Tesla move. I think it's a bit unfair, but this is the accident which we want to avoid. And we can create it, of course, by simulation. This is New York. It's really New York. I didn't know it. My son just passed by and said, oh, that's close to Brooklyn Bridge here. And I checked and it really looks like this. Of course, there is, in the physics setting, in the environment setting, there are things to do. So that's I think that's not important, that's our setup we have. And what we do is we generate clean data because we know where the car drives. With this clean data, we know where it is, what is the environmental condition, and so on and so on. Then we go to a distortion generator, say we distort the data, evaluate with distortion and compare with reference. And then we can say, okay, this is what we want to have or not. So the results should be reproducible. And in the autonomous drive thing, this was particularly important because it might have even legal implications. If somebody has an accident and we want to trace back, was it the AI or something else, then we need to understand where it comes from and make the black box less black box, gray maybe. So we have these scenarios, that's Munich, and that's from a real, so these cars are in reality all real, and we draw them by a program, and we add virtual sensors. We add radar sensors, and we add visual sensors. So this is the same scenario. That's, no, it's not. That's without accident, and it's with rain. You see, this is simulated rain. It's not perfect, but it's as close as we could get with few programming effort. We just used the library which does it, and we can augment it. That's pretty clear. And these are radar data which we distort. So here's the solution to the missing accidents. Of course, we can distort existing data. Like here, this is so-called clutter. That comes from reflection to radar data. And here still we have rain. Why, by the way, radar? Radar is very good because it has a long wavelength, and rain and small objects are not, do not disturb it. This is a disappointingly simple curve, so it's not so nice, but of course, if you go to the OEMs, to the car manufacturers, tell them, yeah, look, this is the bound, you can go. They are very happy. We can, of course, improve our systems just by adding more and more layers. That's our hidden layers, which go from 2, nothing, to 128. This is basically what we did. So we are very happy to have this kind of transition tool implemented. We understand, I think, now most of it. There's a lot of statistics which we can do with it, and we will probably. I think the point is data variability, number of data, size of the model, and hardware needed. These things together will give us a full picture on the applicability of our machine learning models. So the work was supported by 3 grants we had, and these are the references I can give you. Thank you.